to take. Baby, you captivate me. Ooh, with you's where I wanna stay. Baby, you captivate me. Tell me now.
Hello, everyone. Welcome to Workshop Wednesdays. I am Chanel, your host, and also the CEO and founder of Mentor Me Collective. Baby, it's Knicks in 4 for those of you who are tuning in from the United States. For those of you who don't know, the Knicks, honey, we've made it to the finals. First time in 27 years, okay? So coming up with some big New York energy, and we're excited. We're moving along strong, okay? We're going to the chip, and we're we're looking forward to winning it all. But also, welcome to all of you who are tuning in from the United States, from Canada. Please let us know where you're tuning in from. We have some folks from the continent of Africa, obviously folks from the UK, and so on and so forth. So hello, everyone. Welcome. We're so excited. To make sure you tell your friends, make sure you tell your scholar cohort, those who are in your cohort group, let them know that we are live. Let's go Knicks. We have some folks from Kenya, from California. We love that. Hey, folks from India, South Africa, Cameroon, Indonesia, Italy is in the building. We love that. From Nigeria, from Paris. Ooh, Dallas, Texas. We love to see it. Iswaniti. You have to show me how to say that, but that is beautiful. We love all of the countries, all of the representation. And again, we are super excited to have you all a part and tuning in. So please make sure that you go ahead and let your scholars know, let everybody, Lottie Dottie and everybody know that we are live. Today we have an incredible guest. But before we get into that, housekeeping rules. First off, if you don't know, we, Mentor Me Collective, we're partnering with A116Z to do some really incredible events across New York City for New York City Tech Week. So if you have not, if this is your first time hearing about it, please go ahead and visit our website, visit our LinkedIn. I think we also have some stuff posted on Instagram about those two events, one being Code for Climate, where we are building with the incredible Base 44 team, and also powered by Give Butter as well, who will be supporting the solutions that we are building to support climate tech, energy tech, air quality, all that kind of stuff. We're super excited. Also, we'll have some folks from Google there, BP, Pulse, Eli Technologies, the list goes on and on. We also have some incredible founders that will be joining us there as well. So again, tell Lottie Dottie and everybody. Secondly, we have another event for those who are introverts, okay? So, you might be overwhelmed by the content of New York Tech Week, but we also want to create space for those individuals who may be introverts and just want to, kick it and chill. So if you are an introvert and you love board games, we have Board Games and Chill happening on the 4th, June 4th from 11 to 2. So you can spend your lunch hour or lunchtime with us playing some really cool nostalgic games, everything from Uno, Taboo, Cards Against Humanity, and all the things. So we're excited to have you all come and join us in that way as well. Also, outside of that, we did just launch a new newsletter. So we have some incredible individuals who are hiring. So please make sure that you check your emails for our newsletter and make sure that you also apply if you're also in the market as well. So with all of that being said, we have an incredible speaker today. Again, we are partnered with GirlsWhoML. So I definitely want to make sure I take some time to highlight that. They're an incredible platform, especially I think founded out of the UK. And of course, obviously they're expanding their reach around the globe as well. So please make sure that you visit GirlsWhoML to check out their community. Also, obviously, join. And if you are in the UK or where folks are, I think the UK, and then let me not get to telling the story, but I do believe that they have a lot of incredible events happening. I'm actually like in real time trying to Google them, but I did see some really cool events that are happening soon across Tech Week, across I think Ox Tech Week, and things. So please feel free to check that out as well. All right. Officially, we are going to be welcoming Dominika, who is a staff AI research scientist at Iconic. She also has a PhD from the Imperial College of London, where her work has spanned speech AI, privacy-preserving machine learning, and knowledge distillation from large language models. Her research has been published at venues including Pulpit and a I don't want to be butchering these research names. So hopefully, when Dominika comes on, we can talk more about those. But again, we're super excited to have her. It's a pleasure to have her on the stage. Welcome.
Hi everyone. Thanks, Channel, for having me today. It's very exciting.
We're so excited to have you. And again, you have an incredible background as well. So let's start a little bit with that as well. I know you again mentioned that you have been published in several papers. Let us know a little bit more about those papers as well.
Oh, yeah. So, I mean, as part of your academic journey, you publish a lot of papers. So I started with my undergrads. I already had one paper out, and then my master's, and then for the PhD, it's quite normal that you have several of them. And my background has always been more quite diverse. So I have a few publications in speech, adding to speech, but also in security, like you said, with puppets. And so yeah, and also more like healthcare oriented. So my background is quite diverse in that sense.
That's so cool. That's so cool. And of course, your work with Iconic is cool. And of course, I know you'll probably talk a little bit more about that later. But as an icebreaker, if you could describe how you feel about AI with a color, what color would you choose and why?
Yeah, I actually had a few circle in my head, but I think I like blue, just because I associate blue with, it's like blue sky, and it's a color that kind of quite like. It's just very stimulating for me, and I don't really see it as a negative color necessarily. For me, blue is more like an enhancer. Everything is prettier when it's sunny outside.
It's blue and orange skies. I love that. I love that. Amazing, amazing. Well, chat, we welcome you as well to let us know, how do you feel about AI? What color would you choose and why? And while you all respond, I'm going to go ahead and hand it on over to Dominika. Over to you.
Yeah, thanks. Let me switch to my presenter view. But yeah, welcome today to this workshop on compression and optimization. So, like Channel already presented me, I have a background in computer science and AI, and I want to do my PhD Imperial from different intersections of domains. So it was natural language processing, speech, and security, all of this combined, and also add to that healthcare. But yeah, that's one of the story. And then I went on to doing my PhD. I was doing some internship at Amazon at Alexa. So I was working on making the voices a bit more expressive and interesting, and also at Tencent for games. And I'm currently now a staff research scientist at Iconet Interactive. It is a startup, and we have a very ambitious goal of creating new kind of interactive entertainment. And this can be games or movies, but there's a lot of making sure that all of your models and your new techniques that you're developing can also work in practice, right? Because it's one thing that it works in research terms, but now you're putting that out into a product that people will play and use. So it's very important that the practicalities are taken care of. Okay, so actually I can start with a story. Is when I started at the startup, I was working on this great TTS model, which text-to-speech model, that was very expressive. I was quite happy with the quality and the voices. We were great. But when it was time to put that into a demo within the game, that's when things got very difficult. And actually, I'm sure like the software engineer guy that was working on this with me has PTSD from this. He calls back from this model when we talk about like, oh yeah, I have a new model. He's like, is this like this? I was like, no, don't worry, it's not. Because what happened is essentially like I had all of this benchmark that was working for me for research, but then when we put that into production, suddenly things started breaking. So for example, the memory usage actually ballooned because they didn't realize that once you have it over several times, it will start to cache more and more things. Or when we put the model with the game, suddenly the inference time was so slow that it was just not usable. It was breaking the experience, right? And that happens a lot. Especially for me coming from research, I was living in a different world than production. In research, it's quite interesting because you have a lot of problems and questions, But you often don't really think about, okay, how will this run in practice? How does that work? And also an interesting thing is that you have all these benchmarks, that are just metrics, and you're like, cool, we improved that by 2%. You're like, what does it mean in practice? You don't really care about that. You're just happy about, reaching those benchmarks, getting those better values. But in the real world, what matters is like, does this model actually work? Does it give me the product that I want? Does it break the experience? Is it fast enough, or is it so slow that it actually cannot be used, or is so big that it cannot be used because nobody can run it? So all of these questions I need to take into consideration. So with that in mind, there are many ways you can optimize a model and compress a model, and you really can go into a very deep rabbit hole about all of this. But we only have 45 minutes today. So what I would like for you to focus on is just have a clear understanding of what kind of family of techniques I can use. So you kind of build up your tool set. So you can also understand what you could use for your product or for your problem, and how you can compare and combine these methods to actually solve your issue, right? But also I want for you to remember that benchmarking and evaluating is also a very key part of this whole process, and we can have a look at how to go about that. All right, why do we want to compress and optimize? Well, we all have those 240 billion models that are like so great. They improve the accuracy on so many things, but you're like, cool, can I really use that? Well, most of the time, no, right? I always start with the first question is, who is going to be using this model? Usually your target user is going to have a specific model and device in mind, right? Maybe you are targeting mobile users. Maybe you doing electric toothbrushes, right? You're not going to be able to fit that big ass model there. So already there, you want to be able to compress your models to fit within that specific device. If you do go with the big ass model, that means you need to host it somewhere, right? That will cost you money. The bigger the model, the more inference costs you're going to have, and space that you need to hold this model, right? So it's in your interest to reduce the size of your model. Same thing with latency. Big model are slow. So if that's going to break your actual experience within your product, then that's an issue. And you might want to reconsider whether you want to have this big ass model on the server somewhere in China or in US, but you're actually doing that in France, and you had all of the server costs and latency. It's a problem you need to consider. And there's also this ecological factor. I think I like to think that we don't all want to live with data centers. And, if we could reduce the size of these big ass models and just focus on making efficient models, still very good ones, but more efficient, we could also reduce a lot of the CO2 waste that we're generating. And another thing is, you can't really, it's very difficult for you to have any kind of security and privacy guarantees if you're hosting your model on a server. There are more technicalities that you need to consider. Well, it's a very powerful thing to be able to say, look, we're hosting our model on your device. The data is not leaving your device. But that you need to be able to have a small model that fits on that. And also, if your model is quite small, you can also reduce the battery use, which can be quite important once you have some device that has batteries, not necessarily laptops, that you want to preserve over a longer duration than just every day or something. So these are all very interesting pros on why to compress your model. Then the next question is that you need to ask yourself is, what are actually my constraints, right? Am I constrained by memory, by latency, by compute? What is it? So before you go into any kind of optimization and compression, you need to understand what is it that you're trying to build. So that very important question is like, why is it the target hardware? Why is my target user? What kind of device do they have? So that inform how much memory do I have? What kind of implementation, inference engine can I use for this specific hardware? But also, as part of a solution, how fast does it need to be until it breaks the experience? And the same thing in how good does it need to be until it breaks the experience, right? How low can I go until you're happy with this, right? So having all of these constraints in mind and having them in priority order helps you to decide which compression optimization technique you'll be going for. So just a quick example, how fast does your model need to run? Depending on your task, you actually might be looking at different times. So things like live chat, and it needs to be snappy, right? Usually you'll be looking at around 200 milliseconds. But for anything that is a bit more offloaded or that we don't expect it to be this fast, you can then have different the values. But it's important for you to kind of pinpoint what is it that is a good latency for you and keep that as your constraint. Also, how much memory does your model actually need? So imagine you found this amazing model and you're like, cool, but can you actually fit this? So a very neat thing is to be able to compute how much memory your model uses based on the amount of parameters. And this is not necessarily LLM specific, but essentially, you're storing your numbers, your weights in terms of in bytes, so you can compute the number of bytes times number of parameters, and you're able to have that. Then you need to convert that to gigabytes, and that will give you just the amount of memory that you need to hold the model weights. But then comes the cache part, right? Most likely your model will be caching something, and you need to take that into consideration when you compute your memory load, right? And with LLM specifically, what we're looking at is the key-value cache. So basically the keys and the values matrices that you're storing. You can compute that as well with your parameters. And this can be quite a considerable chunk of your memory as well, the bigger your model gets. So I wouldn't sleep on that one and make sure you take that in consideration. You can reduce that cache though by reducing your context length. So like sequence length that your LLM is taking. But yeah, just keep that in mind. All right, let's get into optimization techniques. So as I said, you can really go into really deep rabbit hole for each one of them. But today I just want to give you an overview of the family of techniques. Yeah, because we only have 5 minutes. So let's start with quantization. Essentially, quantization means that you're reducing the numerical precision of your model weights and attention activations to basically reduce the memory storage. So just a bit of a recap on how we store numbers, right? So your models are going to be a bunch of numbers. These are the things that you're going to be storing. And physically, what that means is that we store these numbers in with bits. So you need 32 bits to represent a certain range of values. And you can reduce the precision of how many bits you will use to represent your values, but then you also shorten your range. But very easily, you could switch from floating point 42 that uses 32 bits or 4 bytes, by dividing by 8. And you can have this memory usage by just changing the precision to floating point 16. So it's quite powerful, right? And you can go all the way to int4, and actually there's also, I think, int2. So you can really reduce that range. But what happens when you reduce that range is that you also limit the numbers that you can represent. So with the full precision, you have quite a large scale of numbers that you can represent, right? And but when you go lower to int8 and int4, you can literally just represent from -7 to +7. That's the amount of, you can represent 14 numbers. But so you're cutting your precision quite a lot. But what you will be doing is, when you're doing quantization, is that you're taking this initial range and you're going to be scaling it back to map this new range. So let's say that this is your first range. So it's initial precision. You're going to have a minimum and maximum of the values that you're going to be representing. So let's say it's a tensor within your model. You're going to have a min and a max value. So maybe you only go up to 1050 and then you only go down to -2. That's going to be your range. And then you will map that to your new range. And this is called linear quantization. It's the most commonly used in deep neural networks. And it's very similar to, let's say, normalization in a sense. The same way, once you have like values that go from I don't know, 255, and then your minimal is -10, and then you want to normalize that to 0 and 1, you're basically scaling back your values. And so the way you do that in quantization with the linear quantization is by doing this. So you compute your scale with the min and the max, and then you have a 0 point, which can be set to 0 or can be dynamic, but this all depends on the quantization approach. And so for each of your weight, or each of your number that you're trying to quantize, you'll be performing this affine mapping. And then once you want to bring them back to the original precision, this is what you would do when you do dequantization. And so generally, all the quantization algorithm will have a variation of this, and then deal with these issues in different ways. But that's the base for quantization. And you can do quantization at different times. So the most common one is post-training quantization. So you would have your model. Let's say that you're taking a model that was pre-trained, a big-ass model was pre-trained by somebody else. You can just take that and just cut off the precision after it has been training, so you don't have to deal with that. It's quite cheap for you to do in comparison with the training, but that also means that the harsher you go into the precision cut, the harder also the accuracy loss, because essentially you're just removing a lot of information, right? So it's much harder to represent that information with a smaller scale and range. And that's why some people also suggested quantization-aware training, where you train the model with already this lower precision. Now, how this happens in practice is that you're simulating the lower precision during training, so you actually add additional operations, which makes the model much more robust at inference time to this new precision. This is very expensive to do, right? Unless you have access to the model and the compute, and your model is maybe not too big, you can do that. But most likely with the big LLM or the big model, you will be avoiding doing that. But yeah, so what can you quantize? The biggest win is for you to quantize the weights. So it's much easier and more stable to quantize that than activations. But you might want in some case to also quantize activations. But because they are more sensitive, they require slightly different quantization technique, which are more called dynamic. So static quantization, you could just have your model quantize the weights and you do it. Activation and with static and dynamic quantization, usually this activation will be happening dynamically during inference time, which adds a bit of latency because you're doing those quantization and dequantization operation during inference, and is more sensitive and requires a calibration set. More on that later. And actually, a thing that you can quantize is your cache. It's just a bunch of numbers. In the case of LLMs, it's the KV cache, which is just matrices, right? So you can just cut the precision on that. Surprisingly, the KV cache is actually quite robust to quantization. You can go, I think, quite low. Yeah, it can get you some gain if you need it. So just a quick info on the calibration set. So generally, the models will be using the min-max approach, but there are also more other quantization approaches that will also look not just at your range of initial values, but how the quantization affects the output of your layers, and use that to adjust the scale and the zero. So for this, you will need this very small set. Actually, it's really not expensive to do that. You just need a few examples of your training data or the normal inference data. And the algorithm will calibrate the scale and the zero using this data. So, and a lot of techniques use it. The weights only based don't necessarily use it, but attention one will always need that. So this is just for you to basically understand. You will probably see this quite a lot when they talk about quantization. This basically just means the bits of your weights and the bits of your activations. So with your weights are going to be in 16 bits, you're going to have the floating point 16 or the brain float 16, and then the same for your activations. And then you can go up to lower values. I just want you to pay attention to this. Some of them will have what we called mixed precision. What that means is that within your model, you're going to have different operations that will have different precisions. This is mostly done because some of them are more sensitive. Some operations are more sensitive to the quantization, and actually you want to keep them in a higher precision, which is great. It works quite well. The issue with this is that most of the time you cannot do operation between integers and floating point. So you will need to do some kind of quantization, dequantization anyway, to be able to do your computation, which can add latency. Another thing I want you to think about is that not all of your precision format will be how to say, supported by all hardware. So generally you can go up to int 8 without really thinking about this. Most GPUs will support this, but floating point 8, for example, is not generally supported by your normal GPUs. This is more for like server cluster like models. The newer Blackwell, which is the family of the RTX 50, can support this. But then this family doesn't support the int4 because they're supporting this new format by NVIDIA. So generally, what happens if the GPU doesn't support this is that they will need to quantize and dequantize things into their format that they support. So essentially, this is aiding operations and latency. So something to be mindful about. Just some quantization algorithm. There's quite a lot of them. Usually they come with their own packages, so you can easily just do that, use their code and quantize your models. Some of them will need the calibration set, some of them not. They have pros and cons in terms of how they lose the accuracy, how much latency they introduce. So just it's up to you and to your application and what works for you. My favorite packages are LLM compressors, Autoround, and Bits and Bytes. Actually having even more preference of a LLM compressor and Autoround because their quantization algorithm are pretty good at kind of bridging the gap between the accuracy loss and the latency and the memory that you can get. But yeah, you need just to test whatever works for you in your model. Okay, also one last thing I want you to think about is that so far there's a lot of bias towards, LLM oriented discussion, but quantization works with other architecture as well, of course, because it's just weights. But there are different implications that you need to be aware. So anything that have several steps, so diffusion or RNN-like architectures will propagate errors. So you need to be very careful with the fact that your precision maybe shouldn't be as low because of this propagation of error, accumulation. And generally also some models are more sensitive to noise. In that case, it's more like normalizing flows and GANs. So you need to be aware of that. Maybe you need to train together with the quantization. So yeah, just things to have in mind. Okay, so generally quantization is pretty cool. It allows you to just take whatever model that was pre-trained and just drastically remove the memory usage by half, by 4, and also improve the latency. But it's very cheap because you don't necessarily need to train. But be mindful that it can be sensitive to hardware and of error accumulation. Okay. All right. So now my question for you. Wait, let me switch to this way. Okay. Let's go with the first question. So let's say you quantize your model and you're happy with the memory, the accuracy is too good, but the quantized model is actually slower. What do you think happened? So I give you a bit more time to answer this.
Okay, it looks like two people responded. The first person said maybe it's dynamic, so it added latency. And the second person said, is this because of the type of package used? Some packages may be better at reducing memory usage, but it increases latency.
Okay, maybe give a bit more time if somebody wants to answer. Okay. Okay, so there are good intuitions. So the dynamic part is quite interesting. That's a quite interesting comment. Yes, it could be. Maybe using a type of quantization that is adding dynamic quantization. So it is doing things on the fly, doing inference, so adding operations. Another thing that could be doing that is maybe your quantization format is actually not the correct one for your hardware. And maybe if you were to use that on another one, it would be faster. But for on yours, it didn't match. So the model, the hardware is having to do additional operation to adapt the format to your format. So it's just slowing down your inference. And maybe you're using mixed precision as well. And this is adding some latency. I see already people are answering Q2. Yeah, I mean, yeah. What do you think? Do you think it's better to fine tune before or after quantization? Okay, I see quite some good answers. Yes, okay. So the intuition is that if you can fine tune after quantization, right, you can kind of get back some of the accuracy loss because you can adapt your new weights, your new precision to your domain. So it help a lot. But fine tuning before, you can fine tune before as well, right? It's not frowned upon that this is like the ultimate thing is just fine tuning after quantization. It's just there might be cases when you cannot do fine tuning after quantization, so then you can do fine tuning before. But essentially, the idea is that you can get back some of the accuracy loss, but fine tuning it again after. But that means that you need to have compute to be able to do that, and possibly using QLoRa. Oh, okay. Let me explain VRAM. I see some questions regarding that. So VRAM is essentially the memory that your GPU will be accessing. So you have RAM, which is the memory that your CPU is using, but VRAM is the video RAM. I think I might be making up this acronym. Let me quickly check. Yeah, video RAM. I'm correct. Yeah. Okay, cool. All right. Okay, let's move on. Okay, let's go into distillation. So distillation is essentially the idea of transferring the knowledge of a much larger model into a smaller one. So the smaller one would be mimicking the bigger model that we call teacher. So the way this looks like is that you will have this teacher that will output some kind of response. So you can have the sample response, which, for example, for text, it would be just sentences or text or paragraphs. But you can also have the step back where you get the logic distribution, right? So you would have your whole, tokens, video tokens, whatever the model is outputting. You can then distill the distribution into the student. We can also go do features. Maybe the teacher is generating a set of embeddings that you're interested in. And then you will have the student try to approximate these outputs. So it could be, if you're using a sample-based distillation, then you do maybe cross-entropy. If you're using logits, then you're looking more at Cal divergence, which is a metric to measure the distance between two distributions. Or you can do features, and then you just do maybe cosine similarity or some kind of contrastive losses between the two to try to basically train the student on the teacher output. And there are different pros and cons to the different features you're going to be using. First of all, you need to have access to the teacher, but maybe you don't have access to the teacher's weights. so you can only get the output, right? If you go, for example, Gemini, you cannot get the weights of Gemini. You can only get the output. So maybe you can generate a whole data set of samples in a black box manner. So black box means that you don't have weights access, and then just train the model on that. It's quite nice when you don't have access to the teacher weights, but it's also a bit less powerful than the other, and that the one that uses logit. So if you have the teacher weights and you can extract the logit and the distribution of the response, then you can have a much more powerful distillation of the knowledge into the internals of how the model thinks. But you need to have access, and you need to be able to host the teacher and the student in whatever way to be able to train these things. And feature-based is similar. You need to hold both of them, and then you also need to do the whole training. So it can be quite expensive, but can be very powerful as well. So yeah, just to recap, distillation is a very powerful way of pre-training a model and transferring knowledge from a very large one to a small one. If you were to train the same small model from scratch, you would get worse result than by doing this. And what you can get is, especially when you're trying to make a more specialized model, so maybe you only care about one thing that this big model is able to do, and you just train your model on this one thing, this model will be much better than the large model. But that also means that you're losing generability. So you will be, this model, the small model, won't be performing as well on out of the main samples. So obviously you're losing that. And the most important is that you need the access to the teacher and you're fine-tuning. So if you don't have compute, or if you need to host these big models, if they are big, then you need to consider that into this technique. Another thing as well is whatever the teacher knows, whatever is teaching the student will inherit. So if the model has a specific bias, so if it's always putting like, I don't know, it's always writing with a very high level language, and is, if it's talking the way LLM do, very long verbose, and it's instilling that into the student will be picking that up. So yeah, all right. Some more questions. What do you think is a danger of a weak teacher? Just give more time as well. Yeah, okay, let me clarify what is a weak teacher. So by weak teacher, I mean that the model that you want to use as a teacher is maybe not necessarily very strong in the task that you're trying to train your student with. Okay, we got some few answers now. So one of them is the cascading or accumulating errors leading to a skew model. That is true. And some of the question also say bias. There's a lot of questions that say about bias. Yes, so bias is one of them essentially, right? If your model is quite poor and maybe it's overfitting as well on your initial data set for your teacher, then the student will pick it up. But also, essentially, your student we won't be able to be better than the teacher, right? Because if your signal from the teacher is already bad or weak, the student won't be able to really learn the task very well. Now, you can add reinforcement learning later on, but this still, you won't give you a really good signal. You could use, for example, the teacher, right, to do LM as a judge or kind of judge for your rewards for reinforcement learning, but you won't be getting a good signal. So your rewards won't be as valuable. So essentially, you need to have as good as possible in terms of teacher to train your model. And if you have the choice between two, consider accuracy as part of it, because it's quite important to have very strong signal. Yeah, okay. So maybe we can move on to the second question. I think, yeah, looking in the chat, a lot of these answers are correct. Yeah, that's pretty cool. Okay, second question. Do you think that the family or the types of architecture in this setup matters? Does the teacher and the student need to have the same architecture and the same format for this to work? Yeah, somebody's asking for the slides. I think, yeah, we'll be able to share them, right, Channel?
That's correct.
Yeah. Okay. Yeah, so some of you say no, some of you say yes. So the thing is, no, it doesn't have to be. In the grand scheme of things, the really thing that matters is whatever you're trying to distill needs to be the same. So if it's a feature, like your latent space for that feature specifically, needs to match. But anything around that architecture can be whatever you want, right? The model doesn't have to be the same, doesn't have to be the same family. You could be distilling a vision model with just an LLM or whatever. It doesn't have to be. The interesting thing, though, is with LLM specifically, you actually get better results if your teacher and your student are the same architecture. This is mostly due to the prompting shenanigans of how you're conditioning your models. You can get better results, but it's not necessary. Okay, yeah. Okay. Let me go back to presentation. All right. Oh, and also, yeah, a key thing is that if you are distilling the distribution over a specific, I don't know, vocabulary or set of tokens, these kind of need to match, right? The distribution needs to be the same size and the same and representative. But otherwise, you can do whatever. Okay, now let's go to pruning. So pruning is essentially taking your model and removing whatever doesn't serve you. And you might think that, like, okay, isn't distillation that as well? Like, we're just taking a big model and making that as a small model. And the thing is, yes, actually, distillation is kind of a sense pruning method. But the key difference is that with distillation, you are still trying to mimic the teacher. While with pruning, you don't really do that. You just have your one model, it lives in a vacuum, and then you're pruning the things you don't care about. So there's this distinction there. So what can you prune? Pruning has kind of two families. The first one just being unstructured pruning. So this is kind of a naive approach where you just take all your weights, and then whatever weight is already quite small, you just set it to 0. So if it's already so small, you don't really need it, right? So that doesn't really affect your accuracy that much. But the issue is, again, hardware. Not all hardware support this sparsity. So you might still be holding some memory for these empty slots because it's just of your hardware. So it's cheap and it's neat, but doesn't always work. The other way is structure pruning. So this is essentially removing bits from your model. So it's removing layers, removing the width, removing attention heads, basically literally pruning your model. But the problem is this is very harsh and aggressive on your model, so you will need to fine tune again. Because your model learns all this connection, right? It needs all of these neurons for these connections, and you're losing that, and you need to reconstruct it. Okay, next question. So do you think it is better to prune before or after training, or during? Just leaving more time. Okay, maybe I can answer that. So distillation, the key part of distillation is that you take another model and you use that to train your model. And often your student model is going to be smaller. So there's this element of reducing the model size and pruning it in a way. But the key part is this knowledge transfer. So generally the distillation, that's this family of techniques that does that. But pruning specifically is just taking a model and reducing it. So you could even say that pruning is part of some step of distillation, but doesn't have to be. And it's just like, here's a distinction. Hopefully that was clear. Okay, I get quite a lot of mixed things again. Okay, interesting. Okay, it depends, but most likely you want to prune after training. This is mostly due to compute. But okay, let's look at what happens when you prune at different stages of your model. If you want to do pruning before or during the pre-training phase, this means basically that you need to pre-train your model, right? So this part of the model design and the training that you're removing all of these things. This is a bit of difficult thing because you're already reducing the modeling power of your model before even knowing if you get to your accuracy. You might have several models. Some of them will have more and more complexity than others, but you will need to pre-train every single one of them. And it's not necessarily better because you're reducing the modeling capacity. Now, if you do post-training, you take this model and then you cut off elements of it, you lose quite a lot of connections that you need to fine-tune again. But this will be much cheaper than pre-training your model. And then kind of the middle ground is that you maybe have a model and then you will, during fine-tuning, you can also iteratively prune, but that adds additional hyperparameters that you need to be aware of. So it's a bit more complex to train. So usually the post-training pruning plus fine-tuning is just the most straightforward route. Okay, so quick pros and cons. It can help a lot because you can just cut off all your models. So it helps with the size and the latency. You can also regularize if by just pruning a little bit, but requires considerable training and fine-tuning consideration to do. So of all of these techniques, usually this is a bit more expensive to do. Now, all of these things are things that you can, all of these techniques that I talk about are techniques that you can apply at different stages of the training, but they are more or less separate from the architecture, apart from distilling. But there are specific also architectures design that you can have from the get-go to try to improve the latency or the VRAM usage of your model. One of them is speculative decoding. This is something that you would do once you're happy with the VRAM usage, you have optimized everything that you can, and you still don't have the latency that you need. This is quite useful for LLM specifically, where you essentially would have a smaller model that predicts all the tokens, but then you have the bigger, stronger model that can all at once decide whether they agree or they reject the token. And if they do, then regenerate them. But this speed up the decoding time quite and importantly, and can help a lot to kind of bridge that latency gap. But it does need for you to store this additional draft model that we call the smaller model, and to train it, probably with fine-tuning. Another one is that you have mixture of experts. So within the design of your model, you will have smaller sub-modules that you can activate and deactivate at inference time to perform the task. So you might have experts that you're like, okay, this task is for this expert. So you can just only run your inference through this much smaller path. So it will speed up it quite considerably. You still need to host all of this in memory though. So this is not something that will help you with the memory, but it will help you with the latency quite a lot. Okay, just a quick recap. I have to say that for me in practice, the most useful approaches are quantization, the post-training quantization and distillation. Why? Because these are the ones that get me the biggest gain with a good trade-off in terms of cost. Quantization, very easy, very cheap, and gets me pretty important gains. Distillation is very interesting, but that means I need to have the compute and put the energy into this, but that will give you quite good results once you put that. While pruning is something that is a bit less interesting in terms of accuracy and how much you can get with the VRAM, and a bit more involved as well. And architecture change, well, it's a bit more involved as well. But it can get you quite nice gains if you put the compute and time into this. Okay, so now we have all of these techniques. What I would like to talk about is keeping in mind how to evaluate all your models. Because yes, you can optimize all of this, but it's very important that at each step you kind of keep track of like, okay, how does this perform on the different metrics? And usually you'll be looking at these key metrics, right? First one is the accuracy, the performance of your model. This needs to be done, you're choosing how happy you are with a model, but evaluate this model in terms of within the context that you're using. Because it could be cool that like your metrics are great, your benchmarks are great, but when you put that into the context, you realize actually, oh, well, it's not as good as we thought. It actually fails a lot of the time because there are some environment and context constraints that we didn't think of. And if using any kind of subjective output, so it's like LLM output, image generation, speech generation, please include human evaluation. There is no metric that is actually as good as human judgment, especially if it's for humans. So consider that in your evaluation loop. Look at your memory usage. Usually this is the VRAM or the RAM, but also in context, because maybe it was fine when you would just run it once in an independent environment, but then you put that into your context and you start caching things to make them faster, and you realize you actually need much more RAM. And then same thing with latency. Usually this is time to first token or time to first response. With audio or image, it will be times to first speech, or like just the time to generate the response to the user. Make sure you do that in the context again, because maybe you have an environment that has a specific load. For me, it was a game. The game was taking half of the compute, so actually all of my models were very slow, which we learn after. So yeah, generally keep track of these things. And based on your priorities, right, you will see how you want to adjust your optimization techniques. Maybe you need to improve the latency because it's really important, but then you're happy to then add a bit of more memory consumption just so you can have more latency. Maybe you're caching more things, maybe using the speculative decoding, just for you to balance things out. Okay, how do you profile a model? Actually, if you're using PyTorch, there's a pretty neat package that's called PyTorch Profiler. If you have a neural networks, it will basically give you the inference latency time for in terms of your GPU time or CPU time for each of your models. So this will be the overall inference. So it took 11 milliseconds. But then for each of the modules, it will tell you how much time we spent in that operation. So you can then look at that and be like, oh, okay, well, the attention is using all this time. Oh, turns out it's not using the right attention, or it's a slow one. Oh, I see that my convolution is pretty heavy on this. And then you can try to then adjust your models in that sense, or you can change your models if you're not happy with that. And then, yeah, you can also do with memory. For memory specifically, especially for GPU, I like to use NVIDIA SME and NVTop, which are pretty good commands to just running your thing and then running this, and then you can see live. With NVTop, you can see live the usage. So it's pretty cool. Now, even if you apply all of these techniques and you still don't really get what you need, maybe it's still too slow, and you don't know what to optimize next, then when you go deeper. These are more expensive things to implement. They require some more expertise. That's when you go into creating custom CUDA kernels, which has low-level operation that directly communicate with CUDA and your GPU. Or you can use existing engines that already do all of this optimization for you. This has highly optimized models, most likely for PyTorch, for Linux, that can do all of this for you. It can help you a lot. But they usually require their own format of models and the common model. So if you have anything custom, that's when you need to go into custom CUDA kernels and other optimization. Maybe your attention is slow. Maybe using a slow form of attention, then you need to switch to faster one. You can also fuse operation by reducing then the moment of operation and transfer that needs to be done. But yeah, this is very low level at this point. There's more to say on this. But yeah. Okay, one last question. This is the ultimate question. How would you, if you have this 230 billion models, you love how it performs, and it's a chatbot, right? It's just giving you responses. How would you fit that on a 16 gigabyte GPU that has VRAM GPU, and you still want to keep it quite fast, let's say on the 500 milliseconds? Yeah, so yeah, this is over for you. While you think, I'll answer some questions. So for distillation, can the student model learn the reasoning of a teacher model? Yes, it can. This another thing you can distill, right? You can either do it offline, you can have the model generate that, and then the student will learn it from this, or you can have this online as well. You could, during training, have the teacher generate the reasoning and then have the student try to approximate the reasoning as well. There's a lot of things you can do. Okay, when I have a doubt, if we prune later, won't the model already learn the parameters we are later pruned? Also, how accuracy loss is taken care of after pruning. So yeah, there are two elements to this question. So there's one thing that is quite interesting, is that we have observed that when you train larger models, especially on large data sets, they're able to create kind of sub-network within the network. So, and then by pruning, you can just try to retrieve that sub-network. If you start with pruning and then you train the model, you actually don't know whether you remove the complexity you may want. Well, if you prune after, you let the model decide and learn which activation, which weights are important, and then you can try to remove them. So there's this element there that seems to be working better after pruning. And yeah, how is accuracy loss taken care of after pruning? That's usually when you do initial fine tune. So this is a much smaller and less expensive times of training, where you just the data set is smaller and you don't have to compute for so long, and you kind of correct the accuracy loss, or you at least try to get back to the accuracy that you got. Okay, just give him a bit more time, and then I think we can Oh, okay. Okay, so what I'm asking you to do now is kind of go through the process of how would you try to fit this ginormous model into a small consumer grade GPU, right? What kind of steps would you take to get to that point? And try to use then all the techniques that we have that have presented to you today and see how we can get to that point. Oh, sorry, I just realized there was a typo in my slide. Yeah, that makes it more confusing. Just skip the can fit. Is how would you fit a 250 models on the GPU? Yeah, okay, let's go into the answer. So the first thing is we can combine the techniques that I presented to you. There's not one or the other. We can actually mix them up. So one general pipeline that is actually quite often used is that you start with distillation. Let's start already with the smaller model that we can work with while having the smaller, biggest model that we can work with. So essentially take the biggest memory or latency that you're comfortable with and then distill that from your teacher. What we are quite lucky with is that most of LLMs, like if you go into Qwen's open source LLMs, so like Qwen or Gemma or DeepSeek, they often do the distillation for you. So from their family, you can already pick a smaller model that was pre-trained by them. So you can already start with this point. Now, the next thing you do is you check, am I happy with the accuracy given my task? Am I happy with also the latency? And you check that and you're like, okay, I'm happy with this will be good. But at this point, we still probably cannot or barely can fit this model into our GPU. So the next thing to do is just let's do post-training quantization. Let's go from the brain float 16 to int 8 because we know that this is the most safe quantization. They will work on most hardware, and also we're really not cutting it that much, so we hopefully the accuracy loss won't be that big. We do quantization, we check again, okay, what is the impact? The accuracy may have dropped. The latency has improved because we have indeed halved the model memory. So we're quite happy about that, but we're now not so happy about the accuracy loss. So what we can do is then take this quantized model and further fine-tune that with LoRa or QLoRa in this sense, because we're using the quantization. And and we're happy. And actually here is missing an additional accuracy and latency check and the whole thing, the whole benchmark before we're happy to deploy this. But this is a very common pipeline because it works quite well. Most of the time for your application, this might be enough. Then you can go into deeper things. You can go into like, oh, let's add speculative decoding to make it faster. Let's see if we can maybe distill with reinforcement learning from a teacher to improve this even more. So there's a lot of more things to do, but I think for today, we can stop at that. So essentially the final takeaways I want you, I'll check if there's any question regarding this. Okay, yeah, interesting. Before I move, do you maybe want to spend some time and if you have more question on this pipeline?
I'm happy to have us revisit later on, like during
Sounds good. Sounds good. Yeah. Okay. So let me just the final takeaways. Essentially, the pipeline is just find the smallest, biggest model that satisfies the accuracy, and your latency, quantize that, see if you're still happy with this or not. If not, iterate back, fine-tune it. Maybe you need to distill the knowledge from a bigger model that you're happy with. Maybe that's the original model you can distill from this, improve the accuracy of your smaller model. I would stay away from pruning because it's maybe not as useful, especially when you're not doing your custom models. And again, evaluate every step and use humans. Thank you for listening and pulling up with me this 1 hour here, and happy to answer more questions.
Awesome. Thanks so much, Dominika. This is an incredible presentation. Let's definitely make sure that we are connecting with Dominika. Everything is here on screen. But we did have some questions that came in earlier, so I'm happy to go back to those. And then if you all have any questions, well, I know we normally end around the 3 o'clock mark in the US time, EST time. But I'm happy to, go on for an additional 10 minutes. If you guys have questions, feel free to put them in the chat. Okay, so we had a question earlier on mentioning how does KV cache, how is that generated in LLMs?
Yes, so the KV cache, okay, let's go back to how LLM works. So essentially, you when you do decoding, you're going to have your same input. And for every new token that you're going to be generating, you're going to be creating new matrices of weights, where you will be computing your attention between the first token and the new tokens that you're generating. And for every single token, you're going to have this matrix of, I wonder if it's going to be easy if I can show something. But essentially, you can have matrices. For every token, you're going to be computing the similarity between each and other token. So that makes you these matrices. And the thing is, as you generate more and more tokens, you actually already have computed your a big chunk of your matrix, right? Because that thing didn't change. The tokens that you already generated didn't change. So instead of having to pre-compute that every single time, you can cache that. And essentially what you do, especially when you have prompts, is that as you're generating responses, you're caching this. You can cache a whole prompt, so you don't have to regenerate that. So this is a big thing of LLMs, which was also called pre-fill. That's the stage when you're caching all of the things that you're not going to be reusing. And that helps a lot with the latency. This is really important for that. But then you need to keep track of, okay, I need that much amount of memory to store this with the LLM. Yeah, hope that was clear enough.
I think that was incredible. Thank you so much for the question. We have another question. Would training on a lower different numerical precision harm the model's performance?
It can, yes. You're essentially reducing the model capacity to learn more specific, more detailed representations. But I think until you go to a very low precision, maybe int 8, you shouldn't see such a big drop. I think from floating point 32 to brain float or floating point 16, you should be generally fine with that.
All right. Next question. Why dynamic quantization over KV cache?
Yes. So because your KV cache will be changing with your input. So you cannot pre-compute your KV cache. So you basically be playing around. And also there's a weird thing about the keys and the values reacting differently to how you quantize them. So you also need to do that specifically. But essentially it's because it's bound to the input, which will always be different. And while the weights, which you can do with static, are always going to be there. Like, you just do it once. Your model doesn't move after that.
Amazing. We have another question. I think you actually answered that one. We'll do this one. So this layout for pipelines, is it similar when creating pipelines within data, or is it only just for AI specific pipelines?
So I'm not sure I understand what kind of pipeline with data. Isn't it just like storing data and then quantizing it then? I'm not sure if I will be able to find back the person that asked this.
Oh, yes.
But
can you, oh, sorry, go ahead.
Oh yeah, no. But if it's, for example, you have data, you're trying to store them, then you will be, you're just basically reducing the precision of your data, and you need to see how comfortable you are with losing that accuracy and that information that you're losing. But essentially, the quantization, for example, could be applied.
Okay, it looks like yes, you answered his question. So
Okay.
amazing. Okay, we have another question. Can LLMs be used to build industrial risk mitigation frameworks for autonomous industrial environments, like based on metrics?
So they are used in the form of LLMs of a judge, right? So once researchers are confident enough that they get some kind of good signal from LLMs, they can be used to direct your to build your solutions. But I wouldn't rely on that, and especially things like they're sensitive, like autonomous as systems and environments. You might want to have any kind of verifiable metrics that you know and you trust to balance whatever you're using with LLMs, but it's still very shaky.
Okay, amazing. I think those are all the questions. We have so many folks just saying thank you so much for an incredible presentation. And I absolutely agree. It was so cool. I learned so much as well. Do you have any final takeaways or anything else that you'd like the group to know?
I'm happy to share some resources to dive deeper, and just like for you, if you want to sit down and just try to understand these more, I think I can share that with Channel, and then you can share that with the rest of the cohort.
Absolutely. It's my pleasure. Thank you so much again, Dominika.
All right. Thank you very much, Channel.
All right, everyone. Thanks so very much again for coming to our incredible Workshop Wednesday. Please make sure to know that we will be having one every single Wednesday moving forward. All of my wonderful background. But anyway, looking forward to seeing you all next week. We're having an incredible individual who also is a researcher dive into incredible content around risk mitigation and all that kind of stuff as well. So if you're interested in that, please make sure that you subscribe to our channel. Make sure you give us a big thumbs up as well. And also, if you would like to lead a workshop, we'd love to have you as well. Feel free. Again, now I believe in our newsletter that came out yesterday, there's a link that you all can use to also submit a talk. But until then, again, thank you all so very much. And for those of you all who are, missed her LinkedIn. Hold on one second, I'll bring it back. It's right here. So make sure you take a screenshot. Screenshot. Yes. Make sure you take a wonderful screenshot and connect with the most amazing Dominika. Thank you all so very much. We look forward to seeing you all next week. Oh, and then, just message me in the Slack. For those of you who are in our community, just message me in Slack, and I'll be able to make sure to get you guys the resources that she mentioned. All right. Awesome, everyone. Bye.
Think I've been here before. I know that I must have